So right now we're going to look at traversing our graphs. Just like with trees, there's different ways we can do this. We are going to explore all the nodes in the graph in a systematic order. So the two different types of traversal algorithms that are most commonly used are breadth first search and depth first search. So in breadth first search, that's all going to be a whole lot like depth first search. In fact, the algorithm is going to be almost identical when you code it out. The difference is that rather than using a stack as you would do in depth first search, you're going to use a queue in breadth first search. So the way breadth first search works is that we are going to start at some starting point. Some arbitrary starting point. In our examples will be a node 0. If we're using letters, it will probably be node S as the starting point. So the way this works is that we start at the start node. That's kind of obvious. Okay. Then we visit all our neighbors. Okay, so we visit all our neighbors before we do anything else. Once we're done visiting all our neighbors, we are going to visit all of our neighbors' neighbors. And then after that, all of our neighbors' neighbors' neighbors. And we can't move on to things that are 4 edges away until I visited all the things that are 3 away from me. Okay, so an example of this is this. Let's look at this graph as an example. And we're going to have 3 sets of nodes here. We're going to maintain 3 sets for our information. They're going to color them, but we can't color things, so we're just going to, when we code it up, so we're going to just have 3 sets of vertices. We'll have unvisited nodes that basically we haven't identified that we have to visit yet, or stuff that we need to, stuff that we haven't even seen yet. Then visited means nodes we've completely visited. We've been there, we've done that, we have the t-shirt. Okay. And identified means that these are nodes that we've seen but we've not processed yet. We know that they're on our to-do list, right? Unvisited, they're not on our to-do list yet. We've not put them into our queue data structure yet. So we'll see how this works. So we identify our start node, right? We preload our queue with that one, and then the algorithm is, while our queue is not empty, we dequeue. So we're going to dequeue this, and we put this into our visited sequence. Typically, our output is the order in which we visit these nodes. So we put down, hey, we visited 0 first. And now, since we're visiting 0, we need to figure out where we can go from 0. So we look at all the edges, and we've got 1 and 3, so we mark them as identified. We move them from unvisited to identified and put them in the queue. Okay? So that gives us 1 and 3. Now, it could easily have been 3 and 1, but for our examples here, we will just simply use numerical order if there's any ties. It doesn't matter. 3 or 1 is correct, but for our examples, when there's any doubt, we're going to go in numerical order. So those are our queue. So now we've found all the neighbors. So we've added to our visit sequence. So now we can mark 0 as completely visited. It is out of the running. So now we dequeue our queue to find out what node we're going to go with next. So that's node 1. So now we're at node 1, and we need to find out, so we've added it to our visit sequence, and now we need to find out which of these nodes we haven't seen yet. Okay? So which of these nodes have I not seen yet? Well, let's look at all my neighbors. I've seen 0. I've in fact been there. I haven't been to node 2, so I'll need to add that to the queue. Sorry, and mark it identified. Same with 4, 6, and 7. I'll mark them all as identified. And now they're added into the queue. 2, 4, 6, 7. I'm done visiting 1, so we mark it. So we move it to the visited set. And now we're going to go to the next node in the queue, which is 3. Okay. So now we look at 3's neighbors. 0 and 2, we've seen them all. We've already visited them, or they're already in the queue in 2's case. So we have no need to add them to our queue. So we are done with processing 3. Now we're on to processing 2. So notice that, by the way, we've visited all the nodes that are of distance 1 from node 0. So now we start by visiting 2. Okay, what is 2's neighbors? 2's neighbors are 1, but we've seen that. 3, but we've seen that as well. 8 and 9, on the other hand, we haven't seen, so we mark them as seen, add it to the queue. We have to mark them identified so we don't re-add them to the queue. We're done visiting 2. Now let's go on to 6. 4. I'm sorry, 4 was next in the queue. So we go on to 4. We dequeue, we get 4. We go on to, we check all of its neighbors. Oh, I've seen 1, I've seen 7, and I've seen 6, but I hadn't seen 5, so I'm going to add that to the queue. And we're done visiting 4. 6, there. So next we go on to 6. We haven't seen anything. There's nothing new that 6 will provide us. And same with 7. 7's not going to provide us with any new information. So we've done visiting. So we've visited all the things of distance 2 away. Next we dequeue, and we visit 8. And that has no information to add. And then we visit 9, and then finally we visit 5. So we visited all the things. So we started at 0, we visited 1, then we visited all the things that are 2 away, then we visited all the things that are distance 3 away. And so here's your algorithm for that. And in any case where you would be marking it identified, I'd just be adding that to a set instead.